In this series of videos, we will actually learn how to code and to build simple artificial neural network. So we have already looked into one of the most popular libraries for deep neural network, which is TensorFlow. We will also look into another important library called as Keras before we jump into the coding activities. Now, Keras is a minimalistic Python library for deep learning, and this can run on top of TensorFlow. After the Keras library was published, it soon became a popular library because the API was clean and it was simple, allowing standard deep learning models to be defined, fit, and evaluated in just few lines of code. And the second reason why Keras took off was because it allowed the use of any one among the range of popular deep learning mathematical libraries at its backend, like TensorFlow. So even by using Keras, you have TensorFlow running in its backend. So probably if you are someone who have TensorFlow GPU, we can run TensorFlow GPU at the back end of Keras library so as to make use of the speed of a TensorFlow GPU. So this allowed the power of libraries such as TensorFlow to be harnessed with a very clean and simple interface through Keras. In 2019, Google released the version of TensorFlow called as TensorFlow 2.0 that integrated Keras API directly and promoted its interface as the default or the standard interface for deep learning development on the platforms. And this integration of TensorFlow with Keras is commonly referred to as tf.keras interface or tensorflow.keras interface, where of course TF stands for the short for TensorFlow. There are actually two ways to work with Keras open source project. The first is to use standalone Keras. That is the standalone open source project that supports other libraries like TensorFlow, CNTK, etc. at its backend. Or you could use it as what I have mentioned, tf.keras, that is through the TensorFlow. Right? So either you can use the Keras library as a standalone library as Keras itself, or you can use the Keras library through the TensorFlow backend using tf.keras. And this Keras API was integrated into TensorFlow 2.0. Right? So the focus of building a Keras deep learning model is the idea of what we call as models. So the focus of Keras is the idea of models. And the main type of model is a sequence of layers called as a sequential, which is a linear stack of layers. So you create a sequential and then add layers to it in order in the way you require the computations to be performed. Or in short, one of the main type of model in Keras is the sequential model API. Now there is also something called as functional model API, but we will probably work with this sequential model API. So the sequential model API helps you to create a sequence and add layers to it in the order that you wish for the computations to be performed. We can summarize the construction of deep learning model in Keras under 5 different steps. So the first is define the model. So whenever you are building an deep learning model using Keras, there are 5 steps. First is to define the model, compile the model, fit the model, evaluate the model, and make predictions. So let us start with the first step, which is to define the model. So define the model involves defining the layers of the model, configuring each layer with the number of nodes and its activation function, and then connecting these layers together in a cohesive manner. So as I have mentioned before, in order to define a model, there are 2 ways you can do it. Either by using this sequential model API or to use a functional API model. So in our coding, we will go with this sequential model API approach in order to define the model. So the second step in the life cycle of building a deep learning model is to compile the model. So the compiling the model requires that you first select your loss function. So loss functions are otherwise called as cost function. So first you must choose what is your loss function that you want to optimize. For example, it can be mean squared error, or it can be cross entropy. So if you are performing a regression task, it could be mean squared error. Or if you are performing a binary task, a binary classification task, it could be an cross entropy, right? So the first step is to select this loss function. After that, we require to select an algorithm to actually perform this optimization on the loss functions we have defined, right? So you select your loss function first. Second, you need to select the optimization algorithm which you will be using in order to optimize this loss function. And the choices of the optimization algorithms can be typically the stochastic gradient descent or the Adams optimization. And this compilation of the model also may require that you select a performance metrics to keep track of during the model training procedure. Again, this performance metrics can be the mean squared error or root mean squared error, like for a regression task, or it could be Again, cross entropy, or it could be accuracy or precision or recall or whatever metrics that you need in the case of a classification problem, right? So the compilation of the model has three tasks that is to be done. The first one is to select the loss function, or otherwise called as the cost function, right? And the second step is to choose the optimization algorithm, right? And of course, the third step is to choose the corresponding performance metrics. So performance. So these are the three things that happens during the second stage of building a Keras model, which is to compile the model. Now the third step in the life cycle is to fit the model. So in this step, we train our model on the sample of data that is provided to us with the help of a fit function. So again, when we begin coding, we will see all these functions being used. So using a fit function, we will start to train our model, right? So fitting the model requires that you select your training configuration, such as you have to decide on the number of epochs, the batch size of training, and so on. And what happens during training is training applies the chosen optimization algorithm to minimize the chosen loss function and update the model using the backpropagation of your learning algorithm. So during the compile the model stage, we have already chosen our loss function and our optimization algorithm. So in the training step, which is the fit the model, what happens is that during the training, the chosen algorithm to minimize the loss function using the corresponding chosen optimization algorithm will be applied, right? And usually this fitting the model, that is training, which is nothing but training our model, is a slow part in the overall life cycle of our project development or a model development, because we actually need to start training our model, and this time depends upon either it could be few seconds, or it could be few hours, or it could be few days, depending upon the complexity of your model, the hardware configuration, the size of your training data set, the depth of your deep learning model, and so on. The fourth step is to evaluate the model. So evaluating the model means testing your model, right? So evaluation of the model requires that you first choose your test data set that will be used in order to evaluate your model. And finally, to make prediction using our saved models. So here we will use our model that has been built to generate predictions on new data. So if you wanted to get a list of which are the optimization algorithms available, you could choose from these page. So in this page you will find what are the list of optimizers that you will be using or you can use. So the popular one are RMSE prop, of course, stochastic gradient descent and Adam optimizer. Also, if you wanted to get a list of the loss functions that can be used, again this page gives a good summary of what are the loss functions that is available and which could be used. Now, depending upon the problem you are trying to solve, depending upon whether it is a classification problem or a regression problem, or if it is a classification problem, whether it is a binary classification or a multi-class classification, you will use different loss function. For example, mean squared error is often used when you have a regression model, right? Similarly, you will normally use binary cross entropy if you have a you have a classification problem and it is a binary classifier. Now, if you have multi-class classification problem, you will probably use categorical cross entropy, right? So this page again gives a list of loss functions that can be used to build your model or during the training of your model. And finally, again, this is a list of the performance matrices you can choose from. Again, depending upon whether it is a regression problem or a classification problem, you can choose the appropriate performance metrics. So, normally, if for example, mean squared error, that's something we will use with a regression problem, right? Similarly, accuracy is something we will use with a classification problem. And again, depending upon if you are interested in the precision or recall in a classification task, we could select either the false negative or false positive performance matrices, right? Or you can choose the matrices precision and recall, right? Depending upon which is the one that you pay more attention to. Right? So these are some of the 3 pages which you will find again useful when you start coding. Epochs versus batch size versus iteration. Most of the times I have seen people using these 3 terminologies interchangeably without actually knowing there exists a huge difference between these 3 terminology. So before we start coding, I thought it's a good practice to understand what is the difference between these 3 terms: epochs, batch size, and iterations. So these 3 terminologies comes into picture only when we have a very huge data set. And in the case of machine learning and deep learning, we always have, or most of the time we have, very large data sets. So these are 3 terminologies which we cannot escape from using if you are wanting to build a machine learning or a deep learning model. So it is not possible for us to feed the entire data set into our machine learning and deep learning model in just one go. So what we do is usually break our large data set into smaller chunks and give these chunks one at a time to our machine learning or deep learning model, and based on these chunks of data, we update the weight of our neural network at the end of every step to fit that data set into the model. So one epoch is when an entire data set is passed forward and backward through the neural network. Or in short, one epoch is when we have completed the training of our entire data set once. So if I have 1000 data points and if my model has seen all the 1000 data points, that means I have completed one epoch. So usually one epoch is too big of a data to be fed into a network or into a neural network at once. So we divide that into several smaller batches. Now at this point you might be probably thinking, why do I actually need more than one epoch? So why does it make sense to pass your entire data set through your neural network more than once, right? Or why do I actually have to pass the full data set multiple times through my same neural network? The answer is that for a neural network, when we train a neural network, the data set that we have in hand is very limited. Limited in the sense, even if we have 1 million data point, it is still a limited data set in the eyes of a neural network, right? So always in the eyes of the neural network, however large data set you feed, it is always a limited data set. And we are using the optimization algorithms like gradient descent during our learning process or the training process of our neural network. And we know these optimization algorithms like gradient descents are iterative in nature. So just updating the weights of a neural network with one single pass or one single epoch is not enough. So one epoch often lead to underfitting of your model. So as the number of epochs increases, more number of times the weight are changed in the neural network, and the graph moves from this graph that you can see moves from underfitting to the correct fit or the optimum fit to overfitting it. So again there comes the question, what is the right number of epochs? So if it is too less, it is underfitting. If it is very high, it overfits your model. So you will be wondering, what is this right number of epochs? Now, unfortunately, there is no correct answer to this question. The number of epochs that you will need is different for different data set. But you can say that the number of epochs is related to how diverse your data set is. For example, if you have a data set which has just black cats in it, that means it is not a diverse data set. Now, if you have a data set with black cats as well as white cats, that becomes a diverse data set, right? So when you have diversity in your data set, the number of epochs to train that data set also increases. Right? So that is about epochs. So in short, one training epoch means that the learning algorithm has made one pass through the entire training data set. So next is batch size and iteration. So batch size is the total number of training examples present in a single batch. So as I have said before, you cannot pass an entire data set into the neural network at once, but instead you have to divide your data set into number of batches, right? And the batch size is nothing but the total number of training examples present in a single batch. And you should be aware that the batch size and batch number is two different things, right? Batch size and the number of batches are two different things. So in this case, the number of batches is say 1, 2, third batch, 4, 5, 6 and 7, right? So the number of batches is 7, whereas batch size is the number of data points present in one single batch. So probably if I take this first batch, I might have say 32 data points into that batch, right? So my batch size becomes 32, which is the number of data points present in one batch. And like that, I have 7 different batches. So my batch number is 7. I believe that at this point from your previous course on AI algorithms, you know the difference between a batch gradient descent, a stochastic gradient descent, and a mini batch gradient descent. So a batch gradient descent is when the batch size is set to the total number of examples in the training data set. So that is batch gradient descent, where the batch size is set to the total number of examples in the training data set. Now then you have stochastic gradient descent. Stochastic gradient descent is where you have a batch size set to 1. And third is mini batch gradient descent, which is when the batch size is set to more than 1 and less than the total number of examples in the training data set. So once again, a mini batch gradient descent is when the batch size is set to more than 1 but less than the total number of examples in the training data set. And finally, the terminology iteration. So iteration is the number of batches, right? So number of batches needed to complete one epoch. So you have the 3 terminology: epochs, batch size and iteration. Now let us look into a very simple example. Suppose that you have 2000 records in your training data set, then one way to divide that data set is to have a batch size of 500. So if I have a batch size of 500, that means I will need 4 iterations to complete one epoch. So that is nothing but I have 2000 total records and I am having a batch size of 500. That means in one batch I will have 500 records. So if that is the case, 2000 divided by 500, which is nothing but 4. That means I will have 4 iterations or 4 number of batches, right, in order to complete one epochs.